Okay, so this is the SVM, a sport vector machine. That's an algorithm for classification. So, guys, you can hear me and you can see, right?
Yeah, yeah.
Okay. So, sport vector machine classification is what we actually did in I think last lecture as well. Classification versus regression, right? So this is we this is the SVM is a very good classification algorithm. I mean, this is one of the learning outcome which we're supposed to do accuracy, precision, recall, and F1 on classifications. We already done that, but this is a second algorithm we're doing, and we will have an overview of the kernel methods because last time we didn't touch the kernel in the classification, but this time we'll touch the kernel, right? And that will take care of this learning content analysis concept of introduction to margin based classifier, because we didn't do the margin based, so SVM is the margin based classifier, and I'll explain. But the rest is easy for you, precision, accuracy, and recall. But you really need to understand the margin based and these concept, kernel concept. So it's not very long lecture. It's 19 slides. So I think you will not get bored, because that's why I cut it into sort of smaller lecture. A sport vector machine is a supervised machine learning algorithm used for classification and regression. So you can perform both, and it works by finding the hyperplane, which is a line in 2D or plane in a higher dimension, and that's something I'll explain you here in the next slides, what I mean by hyperplane and what I mean by 2D dimension and what is margin. These are all things I will explain on the next slide. But we need to understand what kind of data we use for this. So this is one of the, this I have implemented this algorithm, so you don't have to do the programming. So I will share with you the code, and I will share with you the graphs as well. So data that we are using is a moon data set, which means we have two colors there. One class is one color and the second class is second color, right? And they are like banana curved around each other like this, right? And that's how the data set will be randomly generated but plotted like this. So you need to define the classification. You need to separate these two color classes from each other. So can you imagine drawing a line like this in the middle? Yes, anybody? Tariq, can you imagine a line there?
Yes, different.
But what would happen when I draw a line? For example, I can actually draw a line. Just give me a second. I have note here, here, right? So I'm gonna go back there, and yeah. So if I draw a line like this, right? Do you think I can separate these classes? Hmm? Is it a
No.
no? I
No.
can't. See, it doesn't matter how I draw the line. There's always gonna be some problem, right?
Yes.
Yeah. So because the data this kind of data set is obviously you can't draw a single straight line to separate them cleanly. So it's a data set is perfect to show why the simple model fails and why we need a non-linear one. So we can't use a non-linear model here. You understand my point? So
Yes, yes.
we need a different sort of like, you know, we need a non-linear model. Not we can't use a linear model because it's not linear. So let's move on to the next one. Uh, before we move on to this concept, how to we separate these lines, you need to understand a few concepts. One is a hyperplane, right? So Atariq, sorry, the Al-Nasari, Nasari, sorry, am I pronouncing your name correct? Al-Nasari, right?
Al-Ansari, yes.
Al-Nasari, yeah. Are you understanding? Can you see this properly?
Yes, I can
Okay,
see it.
good. So let's say you wanna, this is SVM, right? So there are two, three terminologies you need to understand. First is hyperplane, right? This is a simple 2D visual showing a line dividing two colors. You see here, right? So this, the distance between the margins. So here is the margin, right? You see here the margin, and here is also the second one. So this distance, these, I mean, you draw a line in the middle, right? And then you keep this margin between this distance between the two color separators, right? So you draw a line in the middle and then you separate them with the plane, and this hyperplane is from this dotted line to here. You understand my point, right? This is 2D hyperplane, and SVM best hyperplane is the one that gives you widest possible gap. So for example, if the more the gap is here, you see here this one, if this gap is more, right, that means the classes are far away from each other. So think of this two groups of animal, right, and you put a fence between them, and keep them as far away from each other as possible to avoid any mixing. Or think of this as a war zone. The two armies are there, one is on this side, one is this side. So the hyper, if the wider the hyperplane is, better it is, right? So maximum margin classifier is better. You understand my point? And that's the hyperplane. Got it? Everybody understood this? Yeah? Give me sign of life.
Yeah, yeah.
Okay, good. Now, let's move on to the next one. Now, the margin is your safety zone, all right? So the margin is the buffer space on both sides of the hyperplane. Okay. So if this is a buffer on the both sides. So there's a buffer here, there's a buffer here. So this is your hyperplane, and that's the margin of the hyperplane. Got it? Safety zone. So what is the safety zone? If something comes here, it's safe. Something comes here, it's safe because you have this buffer zone. Yeah. I mean, actual divider is in the middle, right?
So it's not really close to the
boundary,
middle line.
Yes, yes. You create a buffer there. So margin is like no man's land. It's like if you go to I think Turkey, I've seen the buffer zone in different countries. That doesn't belong to anybody. So this is the border, and then you have a land in the middle which doesn't belong to anybody, and the army stays on both sides. So this is like a safe zone, where you can keep them apart, right? So this is called margin, the safety zone. And then the most important thing is the support vector itself. The support vectors are the data points that sit exactly on the edge of the margin, right? So if this is a hyperplane in the middle, and that this is the margin, this is a margin, right? This is a soft margin, and the support vector would be here, the closest. Now support vector are those vectors, those are on the boundaries. If you remove them, right? If you remove, for example, this one, this one, this one, these are all three support vector, right? If you remove these three, this line will be moved, right?
Yes.
Yeah. So think of a tug of war, only the people holding the rope at the end of decide the balance, right? The rest are crowd around it, right? They don't matter. For example, if this guy moves from here, this one, yeah, or this one moves from here, would it matter? The line will stay here, right?
Yes.
But if you move this one, this is the closest, right?
It will affect the hyperplane.
It will hyperplane. It will move slightly the other way. So that's why we call this one support vector. This is a supporting vector of the hyperplane. Got it?
Yes, clear.
Okay, good. Now, why perfect separation isn't possible? Like in real world data, often overlaps has noise, right? We can't separate everything perfectly. Some points cross the margin are misclassified. For example, you see here, this is a support vector, but it is a different color, not supposed to be here, right?
Yes.
Yeah. So it's a misclassifier, right?
Yes.
I mean, this is like you divided between this and this is here, so it's a misclassifier. Although these colors are both same. In real life, not all fruits look perfect, right? Some oranges might look like apple, that is okay. We allow small error. So there is a margin of error, and how we actually do across the margin misclassification, we allow them, right? And it's the same way as you allow errors, and you get F and recall, precision and recall, sort of. You remember F1 and precision and recall, where if you make it tight, you overfit, right? And if you lose it, misclassification happens. So let me actually give you a little bit more on the soft margin. It's called, by the way, this is misspelled. It's a soft margin balance between accuracy and flexibility. So if you look at this one, the soft margin allows mistakes, right? So if we have this margin here between the buffer zone, which we called, right? Remember buffer zone? We have a plane here like this, yeah? And then we have a margin line. So here you probably have only, if you draw the actual line, it will be somewhere here, right?
Yes.
Okay. And or it could be on the other side as well. So this is a margin violation, right? But it is a soft margin violation because it is between, I mean, it's supposed to be the other side, but it came this side, but this is still a violation, right? Margin violation. Now, when you set up your support vector algorithm, there are two things you will set there. One, a C value, right? And the second is gamma value. So what are those two values? Because those are the parameters you need to pass, and I'll explain you later on what are those after I explain this lecture. This allows the mistakes. If you set the C margin wider, like for example, you set the C margin 1 or more than 1, 2 or 3, that allows more mistakes because it makes this margin wider. You know this margin? It makes it wider. But what I mean by this, if you go to the previous slides as well, here, right? Here, if you make this margin, this is a margin, right? From here to here. If you make it wider, the margin is wider, right? So you can allow more mistakes, isn't it? I mean,
Yes.
that even if something comes here, it allows more mistakes. But if you make the margin narrow, then the hyperplane becomes very tight, right?
Yes.
And then you basically have fewer mistakes, right? But then it creates an overfitting problem of a risk to fit tightly, the whole algorithm. Now I'll explain in a little bit more detail. So this is about the C algorithm, parameters, all right? When you actually write the algorithm, you need to pass a parameter C. Now the second is understanding the gamma. This is the second value. And I will show you Stanford University live demo of SVM where you set these two values, y, gamma, and also the C. C I explained to you about it makes the plane shorter and bigger. But the gamma is basically if you have low gamma, so you have a smoother curve, gentle curve like this. You see here? This is gentle and smoother, right? Very smoothly divide them. But if you remove the gamma, I mean, but at the end of the day, what are we doing, by the way? Are you understanding, Tarek and sorry, and Mohammed?
Yes, yes.
At the end of the day, what are we doing? We are basically developing a classification. I mean, we have to separate the blue from the oranges, right? These colors.
Yes.
Okay.
Yes, yes.
Yeah. In an ideal world.
So it's very clear.
Yeah. So basically, if you and then when we set up the algorithm, we will pass on the gamma value and C value. So here, if you put the gamma value lower, which means let's say you put it as a 0.1, right? So it will make a smoother line like this. But if you put it very high, like 3 or 4, it will go like zigzag like this, right? It will be ripples, tiny ripples, boundaries, and overreacting, wiggly like this, right? So it is not smooth. So these are the facts, and I'll show you live in a demo in a minute. All right. Okay. So how to use machine vectors now? There are few. Do you want me to show you the code now to actually give you a little bit understanding what I'm talking about, right? And then I can move on. What do you say? I think it's probably a good time to
It's
just
clear.
yeah.
It's clear even without the code.
Okay, that's good.
As
But
you wish.
I think seeing is believing, right? So sometimes you see something and
Yeah.
it's easier to comprehend. So I written this code which I'll share you through the LMS, and if we look at this, right, when we actually create this is a moon data set. See, when we created this is a moon data set we randomly generated through this moon maker algorithm. You see here, and we say we need 600 samples, and we need some noise of 0.2 and random state 24. So it automatically generate this x and y shape for us, and then we plot it on a diagram. So this is how it look like banana, two banana upside each other, right? So two different colors. So we need to separate them. If we draw a line like this, we can't, right? I mean,
Yes.
I did that here as well. So you see here, this one, this is a drawing the line. But if you draw the line and put the C1, and the accuracy is 0.867. Why? It's a low accuracy, by the
Because
way.
it's straight line.
Yeah, because it's a straight line. And the C is 1. What was C? C basically allows the margins, right?
Yes.
So margin 1, the lower the C is, what does this mean? Hold on a minute. Lower the C is, I think this is good spot where we actually do this by live changing the C actually. We can do that. What did I tell you about C here? Yeah, C is about the margin. So wider, the small c mean wider margin, right? A bigger c
Yes.
mean narrow margin. So
Narrow
let's say
margin.
one is perfect, one is a very good value for c. So let's say I retrain this model here, and what I do is I actually put the c value to a little higher. I say c is 5, right? And let's see how much accuracy it gives me. So higher c mean tighter margin. Yeah. Let's see. We run this again, the whole thing, and see what it does. Okay, restart the entire kernel and see. And this is, by the way, we didn't put the gamma yet there, right? We just we're doing the C only. Here we go. The accuracy, oh, yeah. Yeah, accuracy is more or less same, right? On this one. We made the C slightly tighter, but it did not really change things much. Run it again. Going to the 5. See, it's going to the 5. So we made it 1 C again. Yeah, I think it doesn't affect much.
It was 0.873
Yeah,
when C is 5.
yeah, 873, right?
873, yes.
And now it is
867.
0.867. So it is basically from 87 to came to 8. The accuracy sort of like dropped because we brought the C back to the lower. So what did we say about C? Yeah. The small c, wider margin, allows more mistakes, right? So we made the c small, so we saw the accuracy drop down because it allows more mistakes, right? You make it even bigger, it will show you even better. Now this is about this one was about c. Now in the same code, as you move forward, we have this is a linear kernel, right? But we have used RBF kernel, right? I mean, there are two kernels you can use, linear kernel or RBF kernel. Linear kernel draws a linear line, right? Like this, okay? Because you see here the kernel, can you see the code, right?
Yes, yes.
The kernel is linear, C is 1.0, which is lower the C, the more errors can occur, right? Higher the C, less error can occur. And here we this is linear, but RBF kernel is basically that does not draw the linear line, right? But when you do the RBF, you need to provide not only the C but also the gamma, right? So you already know about the C, right? Let's give you what is gamma, okay? So here I gonna explain you about the gamma. So gamma is also a value. If you give low gamma, it gives you a smoother curve. If we give you, because we are doing RBS kernel, what it means is the RBS kernel is not a linear. It's not gonna draw a linear line. It's gonna draw a line which is curvy, right? It can go up and down
Yes.
because that's how it's gonna separate. Because linear separation sometimes is not possible. So that's why you use RBS kernel, you know. And that comes back to our one of our lecture content where we were supposed to discuss different type of kernel. So we're now talking about, so if you keep the gamma high, it's going to be wiggly line. So let me actually explain you here by looking at this RBS kernel. Is this a wiggly line? Is this a wiggly line here, this one? This is linear, right? This is RBS. It's not really a wiggly line, is it, right? It's okay.
It is
Yeah,
somehow, yeah.
but not very wiggly. It's
Yeah,
just,
yeah, yeah.
smooth. It's still very smooth. I'll show you the wiggly in a minute when we go to Stanford University.
Doctor, can you move the meeting?
Oh, sorry. Here,
Okay.
you see here we are setting our SVM parameters C and gamma factor, right? So we're saying 0.1 C and gamma is 0.1, and then we say C should be 1 and gamma should be 0.5. Then we say C is very high, gamma is like 1, right? And
Yes.
and let's see on these three lines, this is how on the same data the kernel perform. Which kernel? RBS kernel.
RBF.
And we by the way use a for loop here. So what for loop does is it's gonna run through this. This is, by the way, in Python, this is called a dictionary. Okay, because if you, yeah, in I think in C language, it's similar concept is in multi-dimension arrays, right? So in the first time when the loop run through this setting, first time it's gonna pick the C value and gamma value, right? Both values gonna pick up, and
Yes.
it's gonna set the C 0.1 and gamma 0.1,
0.1.
and then it's gonna basically this is how you basically call the SVC kernel, right? Sorry, algorithm. And then you pass the, and random state you keep it 42. We discussed that previously as well. We have already X trained and Y trained. We have already done that. We just fit the model, and then we call the predict, and then we calculate the accuracy, and then we print our decision boundaries with the title and everything. So it's gonna create three, because there are three values there. It's gonna first create three graphs. So first graph is 0, C is 0.1, gamma is 0.1. So remember about the C, if you have a lower C, and this is very low C, it's gonna create more
margin.
errors, right?
Yes.
And but the gamma is very low, which means
Smoother line.
smoother line. Yes. So this is a more or less smooth line, right? Not very curvy,
Yes.
but the error is gonna be, so accuracy is 0.85. Then what we do is we set the value of C to 1 and give gamma a bit more flexibility. You understand my point? We let the gamma wiggle around. You see here, it's going here, then it's gonna wiggle, because we set the gamma to 0.5, right? Which means you are allowed to wiggle, right? Here we told the gamma you can't wiggle. You see here? Yeah.
Yes.
Here C mean, oh, allow as many errors as possible, because when the gamma is low, not allowed to wiggle, then you gotta keep the C low, because otherwise there'll be a problem, because there will be with the less wiggling there will be more errors, right? I mean, see how many
Yes.
how many yellow are on the other line, and how many these are. They should be smooth division, right, of the moons. Got it? But it's not. Why? Because we
Yes.
set the C to 0.1 and gamma to 0.1. Muhammad and what's your name? Guys, are you understanding?
Yes, doctor.
Yes, doctor.
All right, good. Now, if we move forward and we set the C to higher 1, which means, what it means, Abdullah? More.
It's gonna be more wiggly and
less errors.
narrower
Less errors,
C
yeah,
margin.
because
Yeah,
we are
less
moving,
margin.
yeah, because we're saying C higher mean less room for
Margins.
margins, yes. And see here, this improves the result, didn't it? 0.97.
Yeah.
Yeah.
Yeah, it did. Yeah.
And because it's, we increase it, let's increase it a little bit more. Here, it's even better classification because we said C is really high, mean no errors, right?
Yes.
And gamma is 1.0, which means you can wiggle a little bit more.
Yes.
Yeah? And that basically, my friend, gave you better accuracy 0.94. So now you understand when you do the SVM model, what is the role of C and gamma, right?
Yes. Clear.
In RBF kernel. Well done. Okay. Now, you need to remember these things I'll ask you in the exam, right? Like we agreed that you won't be coding, but you will be doing the analysis of results, all right?
Yes.
Okay. Now, then we do the confusion matrix on SVM, and we see that on SVM, and that same way, like 0 and 1, two classes, right? And we can calculate the precision recall and all that, and we can draw the proper confusion matrix here. We can come back to the discussion on this later, but let's finish what we started first, all right? Because I'll do the coding with you again in the lab as well. So here now you understand the gamma, right?
Yes.
And you understand the C as well. So C,
Yes.
wider margin, allow more mistakes, right? Small C. But when we made the C10, it really overfit. It like no errors, right? 95% accuracy when you say C10. But then we have to give a bit more wiggly lines. We have to create the other thing higher as well. So how to use vector machines is start with the data in a relatively low dimension, move the data into the higher dimension, and find a support vector classifier that separate the higher dimension data into two groups, right? And in order to move the mathematics possible support vector machine, use something called kernel. So we just, how many kernels are there? Linear kernel and RBS kernel, right? And a kernel function is a trick that helps SVM or other algorithms that can handle complex data that isn't easily separatable, right? So a mathematical tool is used in machine learning, particularly in SVM, to handle non-linear problems by implicitly mapping data into higher dimension space. So here, this is how it's sort of like, this is a two-dimension, right? So illustration of how kernel function project non-linear data into higher dimension, making it separable with the linear boundaries. So here you see here, this is a linear, this is a non-linear separation, right?
Yes.
Yeah. So this made this blue on a higher dimension and separated like this, right? Like this. Got it?
It's clear.
Okay, good. Now, introduction to polynomial kernel. Polynomial kernel is used in support vector machine to handle data that is not linearly possible, right? So in polynomial, you when the way you were passing C and gamma, right? You also pass the D value, which is a dimension, right? So when you say D is equal to 2, it's a two-dimensional data, right? So what is two-dimensional? This is two-dimensional, right? So what is one-dimensional? One-dimensional would be just a horizontal line, okay? So we did the RBS kernel already on two-dimension, right? And we use this, calculate the relationship already. So this what is this right now? Is that two-dimension or one-dimension separation?
One dimension.
This is one dimension. So here, what would be the soft margin here, or you can call it margin, or if we draw on this one, and as one dimension, if we draw a line, where would be that? Here.
Yes.
And the soft margin would be the distance between this and
the green one. Yeah.
Yeah. But if you allow more errors, right?
It will have
you can put the margin here.
Yeah.
A wider margin, right?
Yes.
So if you decrease the C,
it's going to be wider margin.
Wider margin. So it would be from here to here.
Yes.
And then this will be an error.
Yes.
Yeah. Got it? Or it could, if you really see higher, then the line will be here and here, and you'll have these
Have three
errors.
errors.
Yeah?
Yeah.
3 errors, right? But if you want like no errors, then you have to draw a line right here, tight margin. But in the problem is it could maybe overfitting. Yeah? Maybe you miscalculated it. Yeah? With the overfitting problem. So here, similarly, thinking in a two dimension, right? If you have a 2 dimension, you can put it like this, and here you can do the this is a linear, right? And then you can create this is a very tight line, isn't it, right? Classifier, very tight.
Yes.
Yeah. So no margin of error. Anyway, so thank you very much. This was your SVM. Guys, did you understand this? Be very honest. You are honest,
Yes,
guy.
it's very clear, Doctor.
Better than last lecture, right?
Yeah.
Okay, now I'm gonna stop sharing this. Now, what I'm gonna do is I'm going to actually try out something called. I'm gonna just try out the same thing. I'm gonna give you a tool. Okay, it's called. I think it's on the which university is that? The university is Stanford University. Yeah, Stanford SVM live tool. Yeah. Okay, because they have created a live demo of SVM, which you can try out yourself to understand this better. The concept I gave you, right? So just let me pull that. Give me a second. All right, guys. This is amazing. I really like this. Who's missing? Somebody popped out.
I think Abdurrahman is having problem with the
Okay,
connection.
no problem. The good news is this is being recorded, so it should be okay. Right. Okay. So we have here this tool. You see here this tool. This is from Stanford University, right? And it is basically sports vector machine live demo, right? Now we created here you can add data point in red by just if I click it, this is gonna enter red points, right? So I can make red points. I can make the same moon again, right? Remember the moon? Huh?
Yes.
Moon shaped, multiple moons, banana shaped, right? I mean, these are multiple moons, all right? But they are curved. I mean, they are red moons, right? And they are slightly curved. Now that tells me that you can't have good classification, linear classification, because they are sort of curved. Now what I need to do is I need to create another one with a green. So if I want to do the green, what I need to do is I need to press shift and mouse click, and it'll start creating the green ones, all right? Yeah. See, now I'm going to do the classification on this one, right? Let's see how it's possible. Now I got a R, a C, and I got sigma, RBF, sigma, gamma, right? Kernel value. So if I keep the C at this, what does this mean? C is
Default
higher.
margin.
Huh?
If C is higher, it's gonna be more narrow.
But C is not higher, is it?
No.
Right? Because if you make the C higher, you see? No. But then I did not allow curvy, did I?
You have.
I need to allow curve. Okay. Here. Yeah. This is good. Here we go. here I will get a good accuracy, isn't it?
Yes.
So if I put my kernel, RBF kernel sigma 0.63 and I leave the C to 0.25, and if I move C, now this is even better, isn't it?
Yes. Much better.
Yep. C,
You have like one error on it.
yeah, but if the C is higher, what does this mean?
C smaller means wider margin.
Yeah.
Error.
Wider margin, more errors. See, higher, less margin, narrow margin. Now it's making narrow margin. Look at the margin. Yeah. So this is all about. Now this one is with RBS, right? Kernel. And you can actually make linear as well. Yeah. How do I linear? I press the K and it'll toggle with linear. Now the linear is, you gotta make the hyperplane boundaries, right?
Yes.
And this is not, I mean, doesn't matter what, if I do the C higher, yeah, it gives wider margin, right?
Yes.
C
Lower
lower,
C, higher margin.
yeah, lower margin, but this is not a very good data. And sigma doesn't really matter here because we don't pass this one, right? For
Yes.
hyper, it's just the C. Now if I reset this and I create a little bit better classification, like I do this, right? Okay, and then I have on the other side I create green, right? Green would be shift mouse click. Don't worry about it. This is not happening. I'm gonna make I'm gonna check the linear kernel on this one. All right. And see how linear kernel behave. Now I'll press the K. Yeah. Is it a good line? Hyperplane. This is a hyperplane, right?
Yes.
It's a good hyperplane. Look at this, right?
Yes.
And we got a margin allowing the errors. Look at the perfect margin. I mean, this is a buffer zone, so we can tighten it. If we tighten it, if we bring the C
Higher.
Oh, sorry. If we bring the C higher, where's the C? It will make the margin wider. But if we bring the C the other side, less error, no. We need to find it's hard, isn't it? Because it's quite tricky. We need to find a best space. And I think it gave us the best space at C1. Was it C1? Here. Yeah. So yeah. Now here, there are some outliers here, right? This one, this is a noise. That's also an outlier, right? And the rest is pretty much good, sort of like, classification. Sorry, linear classification, right? So do you get the idea now?
Yes.
All right, and you can definitely play around. I will send this. I'll put this on LMS, and I'll send it here in the group as well. You can play around with this and okay, artificial intelligence. There we go. Right. Okay. Good. So I think with this I'm gonna stop recording, right? And then I'll take questions. All right. So that your video doesn't become too